Yeah.
There we go.
Let me start with sharing the screen. Okay. So the topic of my today presentation is Phenix and Superphenix sodium fast reactor static and transient benchmarks. And the goal is to present few open data sets for validation of computer codes for coupled neutronic, thermal hydraulic, and core mechanic analysis for MOX-fueled sodium fast reactors. Because these two systems were this type of MOX SFR, but as you will see, in many cases we can use this data also for validation codes for lead fast reactor, or sometimes even gas fast reactor or molten salt reactors. This is the outline. So as mentioned, it's two reactors, smaller Phenix SFR and bigger Superphenix, both located in France. So for both, I will make a short introduction, and then I would like to present you 5 sets of data for Phenix. These are end-of-life tests. I will present 3 exercises, first called control rod shift for static neutronics, and second is natural convection for transient neutronics and thermal hydraulics, and the third one is co-flowering for static and transient neutronics and mechanics. And for Superphenix, it's the way around: startup tests, fresh core, and then 2 benchmarks, one for static neutronics and second for transient coupled neutronics and thermal hydraulics. So we start with Phenix. This is an overview of this system. It was under operation in France near Marcoule between 1973 and 2009. Was in general very successful operation. And, before the shutdown, they decided to perform end-of-life tests, and this will be the subject. But first, I would like just to remind you the Phenix overall design. This is a classical full-type sodium fast reactor with the core here, small core surrounded by reflector and shielding, 6 intermediate heat exchanger, 2 for 1 secondary loop, so in total 3 secondary loops, 3 primary pumps, then control rod mechanism, rotating plugs, double vessel, and in addition primary containment around double vessel, and the core with diagrid is hanging using conical support collar, not standing on the bottom like in Superphenix. So this is important for thermal expansion modeling. General characteristics. First of all, I mentioned MOX fuel is 23 and 28% plutonium content in inner and outer zone. Then you see thermal power, nominal thermal power, and inlet, primary inlet and outlet temperature. I just indicated these parameters. Intermediate circuit as usual in sodium fast reactor, located, it's called steam generator building with a secondary sodium pump and steam generator. And I will show you more details about steam generator on the next slide, but you can see that it's relatively unusual design, big steam generator. and then energy conversion part. Yes, this is Rhone River, yeah, the nice river close to the reactor. This is steam generator. It's this long system of piping, and the feature is that it's sodium flowing in this piping from above down. Yeah, as you can see here, sodium inlet and sodium outlet at the bottom, and water flowing from down upward, and the water piping, thin pipes are located inside bigger tubes with sodium. So it's relatively unusual design, and the feature is a very big heat exchange surface, as you can see. And for this reason, the whole steam generator is located in the insulated housing with inlet and outlet windows. So convection of atmospheric air through this steam generator housing allows to remove decay heat from the surface. So there are windows which can be opened by operator manually. So as far as I know, there are 4 tests published. The first one is this symmetric test, which I did not participate in and did not include in this lecture. But 3 others is, I already mentioned, control rod shift, natural convection, and co-flowering test I will present to you. I start with control rod shift test. This is a Phenix core map. The color code is for inner core and outer core. These are fissile cores with different plutonium content, and it's surrounded by blanket, fissile blanket, and reflector and shielding. There are 7 control rods, 6 in this ring. 6 are control rods, and central position is safety rod, which was not used in this exercise. It was out of the core. So there were 4 steps for this exercise, and every step was different from viewpoint of axial position, of axial pattern of control rods. The important feature that reactor power is always kept the same. So when one control rod was inserted, then the perturbation were compensated by others, to get the same power. And you see these 4 steps. The first reference one was when all control rods are at critical position, at the same axial position. Then the blue rods was inserted, blue one is here, and the rest were slightly withdrawn to compensate. The third step, the blue is inserted, red is withdrawn. The insertion of blue was compensated by withdrawal of just one red. And finally, the red was withdrawn and all others compensated positive reactivity. So the idea is that we have at the outlet of every assembly 2 thermocouples, and temperature were measured at every fissile subassembly for all these 4 configurations. And then we converted the readings of thermocouples into delta T and then into the power. So we had power map for all these 4 steps. And what we did, we used 3 data sets, which is a difference between step 2, 3, and 4, and 1. So 2 minus 1, 3 minus 1, 4 minus 1. Numbering here is important. So the central central safety is 1. And then we go by rings. The first ring, around the clock, the second, and so on. So when I present you the data, then it will be numbering of fuel assembly. So you should go in your head by these rings, yes? So this is deviation of step 2 from step 1, and this is power deformation for step 1. The cross is a measured value, the red symbol is trace sparks. This is US NRC system code coupled with reactor kinetics code. And the blue circle is ERANAS. This is CEA fast reactor code. Okay, you can see this typical shape. Yeah, these waves when the bottom points are those assembly around inserted blue control rods. And you can see the agreement. Yes, the level of deviations, the level of errors in this, once again, change of power between perturbed state and reference state. The second one is one on one side is injected, another is withdrawn. And we have more linear perturbation between these 2 points. So one is increased up to 10% and injected is deformation minus 10%. Again, we have quite reasonable agreement between measurement and predictions. And final one is withdrawn red. And again, we have another shape, yes? So 3 sets of experiments. What is added value of this data? We have data sets on temperatures at each fuel subassembly outlet, and we can use this data to validate our code's capability to predict consequences of small axial shifts of control rods. They're asymmetric or they can be symmetric, and still it gives us confidence, yes? And this is especially important for fast spectrum cores because of stronger interaction between control rods compared to thermal cores. And also from viewpoint of safety, we have higher importance of reactivity feedbacks driven by differential thermal expansions compared to thermal cores. So differential thermal expansions leads to shift of control rods, yeah, with respect to fuel. This is a result of IAA cooperative research project. And we issued this tech doc, which is open publication, and you can find here detailed specifications, test data, and results also of all codes predictions. The second exercise is natural convection test. It's also one of the Phenix end-of-life tests. So I already showed this. We see here primary and secondary system of Phenix. And I use it to explain the steps, the phases of this test. So it started with feed water shutdown. So here, phase 1, they stopped shutdown. They stopped supply of feed water to steam generator, and this was in fact unprotected phase, unprotected loss of heat sink. Yeah, it's resulted in increase of inlet primary temperature at the core inlet, and it was 8 minutes before the scram. So we have 8 minutes data for unprotected loss of heat sink. Then after 8 minutes, scram operated and the primary pumps stopped, and secondary pumps strongly reduced the rotational speed. So now this unprotected loss of heat sink becomes protected loss of flow. Then it was for about three hours, yeah, without circulation, and idea is to measure, to test the transition from forced to natural convection, both in primary and secondary system. And after 3 hours, they opened steam generator casing, as I showed you, and this was the final heat sink for decay heat. And then for 4 hours, the atmospheric air circulated through this box, removing decay heat. I show first the phase 1, unprotected loss of heat sink. So you see the level of power and flow rate. Inlet temperature was 360. You see here the measurement of core inlet temperature. So the perturbation was dry out of 2 out of 4 steam generators, and as a result, increase of inlet core temperature by about 40 degrees. And after 8 minutes, scram was actuated. We created very simple model for trace using point kinetics. It was just 4 parallel channels. It was only for the core. We used heat structures to model fuel, but also digrid. And we used coolant temperature and flow rate as boundary conditions and coolant pressure at outlet. The interesting was that we model fuel in a simple way, but in 90% of fuel assemblies, we assumed closed fuel-clad gas gap, and in 10% we assumed it open. And in fertile blankets, we also assumed open gap. As I said, we use point kinetics model and simulated Doppler fuel expansion, axial, digrid radial expansion, and interestingly also the axial vessel expansion. Here is the results. On the left, you see reactivity versus time and power versus time. The data we have for reactivity with black circles, and power also black circles with some uncertainty. So we obtained good prediction of the reactivity with less than 3 PCM error. And also power. We used not only point kinetics, but also trace sparks, which is 3D diffusion, kinetics solver. From viewpoint of decomposition of reactivity, we see that digrid radial expansion is most important and driving feedback. It's negative because temperature grows by 40 degrees, and it's compensated by positive Doppler and positive vessel expansion. Yeah, vessel is heating, and in about 2-3 minutes, it starts to expand downward, and the core goes down also, and it results in slight withdrawal of control rods, and we can see in green the clear positive vessel expansion component. Fissile and fertile fuel zones bring opposite feedbacks due to axial expansion according to our calculations, because we are heating, in fact, fertile fuel, and it increases the size. Yeah, it expands axially because temperature is increasing, but because of the reduction of power, the fissile fuel is decreasing the temperature, and it results in negative feedback, and in combination the effect is small but still negative, as you can see here with spin curve. Yeah, we performed a number of sensitivity studies to accurately predict core inlet temperature. Gap conductance is very important here, and fuel expansion mechanisms. Now this is results before I showed you phase one. Yeah, you can see here phase one in red, but the first on the left. But this is results for the whole test. And we did the exercise for the whole test, which is not now neutronics, but pure thermal hydraulics. So we have power, which is specified now from experiment, this unprotected part, then scram, and then decay heat part. Yeah, and you see flow rate evolution as calculated, because for primary for primary system we don't have reliable flow rate measurements. It's logarithmic scale, as you remember 8 minutes, 3 hours, and then 4 hours. And here I summarized the results of the prediction. On top plot, it's calculations. On bottom plot, it's experimental measurements. And you see here core outlet temperature, I-checks outlet, and pump inlet. And in general, we can see that for the initial part, the flow rate is constant, we have reasonable agreement. And then for established natural convection, we also quite good with prediction of the rate of the temperature decrease, and correspondingly we predict reasonably good decay heat removal by atmospheric air convection through the steam generator casing. And the biggest difference is in transition between forced and natural convection. And this is not surprising because we use trace, which is basically one-dimensional code. So we need here, and we used in the exercise other solutions were done with CFD, and you can find the results in the tech doc I will show in a moment. But from viewpoint of added value, first we have data on total reactivity and reactor power for validation of coupled neutronics and thermal hydraulic transients without scram. In particular, with emphasis, we check reactivity feedbacks, Doppler and thermal expansion effects from radial expansion of digrid and axial fuel and vessel expansions. And from viewpoint of the whole test, we have data on primary temperatures to validate three-dimensional thermal hydraulic transients and pool type fast reactor initiated by loss of flow in presence of decay heat. And we have many temperatures measurements I showed you, but also there was a poll of thermocouples in cold pool, and there is a nice data on thermal stratification, which people modeled with CFD codes. Again, it was IACRP for several years with many participants, including, of course, US Argonne National Laboratory. Again, it's openly published document. You can find a lot of results, specification, and test data. The last test I would like to present for Phenix is co-flowering test. And the purpose was to investigate co-compaction in sodium fast reactor and assess neutronic consequences of mechanical core deformation. So in pile device was inserted in the Phenix core center, as you can see here on the right, for mechanical core flowering. The assembly displacement, flowering forces, and the reactivity signals were measured under different temperature conditions. You can see here how this device in the center worked. So the force was applied axially, and then the devices pushed the first row of assemblies radially, and Phenix was a freestanding core without core restraint system. So then we have flowering effect. So our plan was to develop methodology of coupled neutronics and mechanics analysis, calibrate using data, this modeling, and then model transient. Yeah, so we would like to deform and then release and see how it will be in transients, because test was only static. For different configuration, they measured values, but there was no transient test. And our plan was also to qualitatively compare our results with negative reactivity events measured in Phenix. It's IANS, and this is French abbreviation. I will show you a slide. So our methodology was to use Autodesk inverter Nastran, which is allows us dynamic mechanical finite element calculations. So we provided force, then we produced core geometry snapshots and feed them directly to Serpent Monte Carlo code, and then for every snapshot we calculated reactivity. And then we take this reactivity as function of time, and we feed it into a simple reactor kinetics, point kinetics calculations to predict power. So we used here the data we obtained in the first test. I presented control rod shift, neutronics, different kinetics parameters, and so on were produced based on another test. We did sanity check just to be sure that our interface between Nastran and Serpent properly worked. So we make text-based input for Serpent and then used also interface, which allows directly send geometry from Nastran to Serpent without input, and it's showed us good agreement. So first we calibrated assembly top deformation as a function of vertical piston displacement. So these are data when we push it here, and then what is the deformation, what is the displacement. There are measurements, and red points is our predictions with Nastran. And then we also calculated with all methodology with Serpent the reactivity effects. And again, we are in very good agreement. We catch this negative reactivity effect because we increase the amount of inter-assembly sodium. And this is slowing down the spectrum. And this is negative effect. So we calibrated Young modulus of homogenized subassemblies to reproduce deformation measurement with Nastran, and then we done Serpent calculations and get good agreement. And then, as I said, we made this deformation, and then we released all restrictions, and we obtained Nastran predicted as the transient. And this plot shows subassembly displacement versus time for different subassemblies. So we see the propagation first of the first ring, then it hits the second ring, and then they go back. So this wave distributed radially. And we take snapshots and obtain the reactivity. And in black, you can see this wave of reactivity, it goes down, and then when assemblies go back and compact the core, we see the positive wave, positive hump. Then we feed it reactivity into point reactor kinetics and obtain the power. So this is a power shape. And then as planned, we wanted to see how it correlates with this our events. There were 4 events with sudden negative reactivity insertion and shutdown of reactor in 89 and 90, and 2 last events were recorded neutronic signals, so they are shown here. We have power, and we considered our predictions shown in green here with measurements. And we saw this not ideal but surprising correlation, at least for the first phase. I must say that this is one of the possible reasons of these events is mechanical core deformation, probably because of sodium boiling, and collapse of the bubble created this pressure pulse, which created this similar what we model, the perturbation. So we decided to make a sensitivity study, and in our end-of-life test, it was isothermal test, and the distance between the top pads was set to 0.25 millimeters as hot zero power. And we used this approach first in our exercise. But then we decided that the Phenix event, negative reactivity event, was at hot full power. So we decided to reduce the distance to 0, because they should be in contact when there is an axial temperature gradient. And we did again this exercise, and as you can see, it's slightly different history, and we compared again, and we received even better correlation with results. So added value of this exercise is that we have data on forces, displacements, and corresponding reactivities to validate core mechanics and neutronics coupled for freestanding fast spectrum cores. In particular, it provides radial deformation pattern and geometry versus applied axial force, reactivity response to flowering deformation, and it's important for understanding negative reactivity events at Phenix. There was no CRP, but these are reported in Ph.D. thesis of Janusz Body, defended in 2022, and this document is available openly, and you can find more data and results on this test in chapter 3, and also more on transient modeling in chapter 4, and you can find more references there also. Okay, I should continue with Superphenix. It was a larger reactor also in France, operated between 1985 and 1997 in Cremalville, close to border with Switzerland. This is a bigger reactor, the biggest as far in the history, with 3000 megawatt thermal. Again, I highlighted here inlet outlet temperature. It's MOX fuel with this lower plutonium content because the core is bigger compared to Phenix. So 2 startup tests we created and analyzed. First was static neutronics, and second transient reactor kinetics. This is a core radial map for Superphenix. Again, we have more here, the control assemblies, but otherwise it's inner outer core, radial blanket, and then reflector. Here is the axial structure of different assemblies. And this is a list of 13 configurations we formulated. The 6 for cold zero power, then 5 for hot zero power, and then 2 for hot full power. Different temperature, different position of control rods. And these are results for K-effective. So we have 6, 7 solutions compared to reference one done with Serpent. Good agreement in principle. The biggest discrepancy is, of course, with injected control rods, which is difficult for diffusion codes. Power distribution in blue, and in general, it's plus minus 2%, the discrepancy. Doppler constant also quite good. Void effect zone-wise, much more difficult and higher discrepancy. Again, it's challenging for diffusion codes. And as added value, it's relatively simple, straightforward exercise, but we don't have around too many benchmarks, well-defined benchmarks for static neutronics code for large fast spectrum Oxfield core. So this one is published and available. You can find all results, all specification in this paper of ASME Journal of Nuclear Engineering and Radiation Science, which the whole issue, by the way, was special issue to report the results of our European project called FASMART. And this paper, Superphenix benchmark, consists of two parts. The first part is static neutronics, and the second part, as I show in a moment, will be about transient reactor kinetics. So here, what we did, we collected papers from from time of startup of Superphenix. They published the results of startup tests, transient tests. So we collected just figures and digitized them and used them for modeling. And we used reactivity coefficients and kinetics data calculated by static benchmark. So everything is consistent in this sense. We created more or less simple model similar to what we used for Phenix. This is core only with some heat structures for fuel, but also for out-of-cost structures like Vessel and Stromberg. Yes, we used point kinetics here with reactivity feedbacks, basically Doppler, and many thermal expansions of many materials. So I have now the list of all 6 transient. I will go very quickly. And first, I would like just to say that there is 3 reactivity insertions plus positive reactivity insertion from hot zero power, and then 2 negative at different power levels, then 2 tests with primary mass flow rate reduction, again at different levels, and then inlet temperature reduction, the 6th one. Here I put them as overview as a function of reactor power and inlet temperature. So you see here the group of 3, 2, 4, and 6, because they were performed one after another different perturbation. Then at high power, we have 3 and 5, and at 0 power, the first one. So the positive reactivity insertion plus 30 PCM, isothermal, we have relatively simple increase of reactor power and then decrease due to reactivity feedbacks. So this is extremely tricky, extremely difficult to get, because you have to very accurately predict the fuel temperature evolution and gas gap conductance in order to catch this reduction of power, and we get good results. So I present here the result of 3 code trace, US NRC, then Germany GRS Athlete, and Germany KIT CMSFR code. So here are details of reactivity components. So it's mainly, as I said, negative Doppler, which compensate positive reactivity insertion. The second exercise is negative reactivity insertion. It's minus 50 PCM at 23% power. And here again, the picture is reversed. We have reduction of power, and then it goes up and then stabilizes due to reactivity feedbacks. And here also we have similar picture with now positive Doppler and quite strong control rod drive line expansion because of increase, because of change of the outlet coolant temperature. Then case 3 is negative reactivity insertion in 3 steps, 25 PCM each at higher power level, 50%. And again, we have similar picture, but with 3 steps. Physics is similar, and the good point is that we can check the performance of our codes in similar conditions, but at different levels of power and temperature. Then primary flow rate reduction, we have 2 cases at different powers. This case is reduction of primary flow rate by 10% and reduction of inlet coolant temperature. And we have this complicated wave reduction, then increase, and then stabilization, because we have competing events of increase of inlet temperature and also deterioration of heat transfer. So the Doppler is also quite complicated, but also here we see clear digrid radial expansion, differential control rod expansion also quite complicated, which involves vessel expansion, control rod drive line expansion, and of course fuel and cladding expansion. So quite complicated combination, and with our simple model, we are able to catch all this interplay properly. Then in other case, again, flow rate reduction at different, at higher power level. Here we see similar physics, but we also see perturbation when the change of coolant rotates through the primary circuit that enters again the core. We see these waves. Similar, okay, it's quite busy, but it's a similar interplay to previous one. And finally, case 6 is inlet temperature reduction, which is quite similar to Phenix exercise I presented you at the beginning, but the reverse direction. There was inlet temperature increase, and here it's reduction by 10%. And the result is that power goes up and then stabilizes. And here mainly we have a differential control rod expansion, and it's driven also by digrid radial expansion. Okay, this test, SPX transient benchmark, has added value. We have 6 data sets to validate coupled neutronic and thermohydraulic one-dimensional, basically transient behavior of large SFR. It includes complicated interplay of many reactivity feedbacks, including Doppler sodium density and thermal expansions of many materials, fuel-clad digrid, and out-of-core structures, including CRDL, strong back-end vessel. So as I already mentioned, you can find all details, including all data of our what we measure, what we digitize, yes, from journals in this publication in ASME, Journal of Nuclear Engineering and Radiation Science. This is, by the way, open source journal. And now it's time to summarize. So several data sets for MOX-fueled sodium fast reactors are available in open literature. They include specifications and measurements, and they can be used for validation of coupled neutronics, thermal, hydraulic, and mechanic calculational codes. So with this, I would like to thank you for your kind attention, and also my thanks go to CEA France for sharing Phenix end-of-life data, for IEA Technical Working Group on Fast Reactor for CRPs we have, and in particular to Aurelia Sheno, Janusz Body, Alexander Ponomarev, Evgeny Nikitin, and Emil Friedman for our cooperation. Thank you very much.
Thank you, Dr. Mikityuk. We've got about, well, let's see, 38 people still on, but we've got some questions already in the chat. Mark, go ahead and unmute and ask him that.
Okay, yes, thank you for the presentation. It's very interesting. I learned a lot. I am the chair of the International Reactor Physics Evaluation Handbook. This is Mark DeHart. And I was wondering if you consider compiling a benchmark specification for Phenix and Superphenix to be able to put into that benchmark collection. It would be, it's certainly a value to the US for reactor licensing, but to the international community as well.
Thank you very much. I think it's a great idea. So I think for Phenix, especially control rod shift, test is very relevant for handbook because it's official, it's very well documented, and well, it's already published. Everything is available. It's basically a question of agreement and editorial work. For Superphenix, I think it's more complicated. As I mentioned, our concept, our approach was to work only with openly available papers. So we did not contact EDF, Framatome, or CEA. We did not obtain anything from them. So we just collected papers, and from all these papers, we tried to create the complete set of data. Yeah, but because of this, we cannot say that this is official, this is real Superphenix model. And we digitize curves from the, from papers from journal. I'm not sure if we can publish such uncertain data in handbook, but definitely we can discuss it. I'm happy to discuss this and see what we can do.
Yes, I agree. I'll follow up with you directly on this. And I agree on Superphenix. It may be difficult, but EDF, possibly talking to EDF, me talking to EDF would be an option. Thank you.
Sure. Thank you, Mark.
Any other questions for Dr. Mikityuk? I would ask if it's okay if we share the video and your slides on the IANS Idaho webpage.
Absolutely, yes. I will send you PDF
Excellent.
of the slides. Mm.
Okay.
I had a quick question, if that's okay.
Please do.
So maybe the difference isn't that significant overall, but I noticed that in the Phenix reactor kinetics test, I think there's a slide where you're comparing the experimental results to 0D trace and 3D trace Parks results. I was curious why the 0D code performs better, it seems. Thanks. Thanks for the presentation.
Thank you. Well, it's, I think, very common joke or wisdom that point kinetics performs better than special kinetics, because, well, you can, in particular in fast spectrum system, because you can prepare very accurately the reactivity coefficients with Monte Carlo code. As a result, especially in this case, the deformation of power is very insignificant. And point kinetics is a very good assumption, in fact. While in special reactor kinetics, we have errors which are introduced via parameterization of macroscopic cross-sections. So we have, in particular in trace parts, we used quite simplified approach based on first order derivatives. So in this way, we introduce an error. That's maybe it. I could not give you more. It's relatively difficult to give you more exact explanation of this discrepancy. Thank you for this.
That's great. As a CFD focused student, this was helpful. Thanks.
Thank you. So I see the hand raised. Please.
Oh yeah, my name is Donglin, and thanks for the great presentation. You really helped to understand our flow and really great work. Thanks. And I have a real simple but quick question because I'm not familiar with the design adopted in Phenix or Superphenix, but looks like dimple or restrainer is adopted in both design, because looking at your description for flowering effect, looks like there's some dimple attached to the surface.
Yes. You mean pads, yes?
Oh yeah.
This, we call it pads, yeah. Dimple or pads, yes. They're at one axial level, there is these devices touching each other, yeah.
So
to provide the distance, yes, the gap between assemblies.
So these reactors do not adopt wire wrap design, or is it just for restrain some expansion?
So your question, why these pads? These pads are to prevent compaction. Yeah, they guarantee the distance between sub-assemblies.
Oh, assemblies. Okay. I thought it was field pin. Thank you.
Yeah, this is a main goal. Yes, against compaction.
Okay, any other questions? Got just a few more minutes. All right, well, if not, Dr. Mikityuk, we thank you very much for presenting this. I will get the video and slides posted to the IANS Idaho webpage as soon as we can. And yeah, thank you. And stay tuned. We'll announce our next Lunch and Learn, and hoping to get a dinner meeting scheduled very soon.
Thank you, Joseph, and thanks everyone for inviting me here and for your attention. Have a good day.
Very pleased you could join us. Thank you.
Bye-bye.